It's weird. Your class isn't listed on our Tuesday schedule for some reason, so I'll take care of that. That's on us. That's not you.
Next Tuesday.
Yeah.
Yeah, but it's canceled, right? Maybe you guys.
Yeah. No. Well, yeah, but it would still show up on our schedule.
Oh, really?
Yeah. But that's like I said. That's us. It's not on you. That's
okay.
Something that I think we triggered. So. But.
So to be clear, this recording will go up today, right?
Correct. Yeah.
And then there's no recordings at all next week, Tuesday or Thursday.
Yeah, because you canceled class all next week.
Very good.
We have those taken care of so that they won't record. The Zoom meeting is canceled so that it won't technically happen. So you won't get those recordings either. So.
And then the following Tuesday, it starts up again.
Yeah.
Right.
Correct.
Thank you.
You got it. Everything been good so far this year?
Yeah, it's been great.
Awesome.
Equipment's very easy. It starts recording without a hitch, so.
Everything else kind of working for you. You know how to use your tablet like you want to.
Yeah, everything's good
awesome.
So far. At first I didn't know if this camera could move.
Yeah.
And someone complained in the online. They're like, every time you go to the board, I can't see you. So then I figured it out, and I was able to steer it over there. One thing that's kind of a bummer, if you will, is whenever you turn this on, it darkens over here. Wait, why isn't it full screen?
That's a resolution on your iPad.
Yeah, but I do the same thing every time. It's always full screen. Oh, there it goes. Okay. Yeah, see how it got all dark over here. I don't know if you guys can get another light or something.
Well, we can't right now. The building lights are down.
Oh, really?
Normally, these two lights right here would be on.
Oh, yeah, that would make a difference.
They don't work.
Okay.
It's a complaint that facilities knows about. So the whole building controller is running off of a Windows 95 computer that broke. And so we're having to replace a module that works on that. So,
okay.
Well, I should say we're not having to. Facilities is having to replace it, and they're having a problem finding the part to fix it.
Oh, okay. Yeah, 95. That's old.
We are. So you would like to have a tracking camera working on you the whole time. So we're working on implementing those in a lot of our rooms. We've only got a couple of our rooms that are using them right now, but it's nice to hear that more and more instructors would like it, because we always thought that for a while, a lot of our instructors thought it was distracting, and that it would be like they feel like they didn't want it to constantly move. But we're kind of seeing a switch where a lot of more instructors are wanting that, so they feel a little bit more free when they're teaching their class. So that's a good to know. So that's one of our renovations that we're looking at, is putting more and more tracking cameras in the class.
That'd be great. And the option to keep it fixed or track, right?
Yeah, absolutely. We would have the option for people to turn it off if they want to, or leave it on. So
yeah, I think it's a good idea, because the lectures are dynamic. You come over here, write something, you might go over here and point.
Yeah. So we do have one in 1030. And then 1050 are our two tracking cameras right now. So
very good.
If it's something that you really, really, really like, you normally teach them 1000, right?
Mm-hmm.
Okay. There's a possibility we might be able to move it or get one in mid-semester. We'll see.
All right.
I make no promises though.
All right then. Thank you.
You too.
What's up, Chalfan?
Yes.
How's everything going?
Good.
How about the program you want to work on today? Yeah, that's gonna be we gotta figure out all that indexing and stuff, and then I think we'll be all right, at least with the EFIE. I think the MFIE is very similar. There's just a polarization change and some constants, right? So we probably could reuse a lot of those functions.
Not quite. For the EJ and the HM, it's not actually the same.
They're not the same, right?
Yeah, they have divergence of divergence of.
Oh, the divergences are there?
Yeah, there's a gradient of divergence of something, but for ZJ, because it's in X, JX prime, but the divergence is for Z or something. So that's why it's cancelled.
So ZHJ.
Yeah.
The magnetic field due to J is in the plane.
Yeah.
So then you probably need the divergences, right?
Actually, that's one is the HM.
HM?
Yeah, because you remember ZG is 1 plus gradient of divergence of something.
Yeah.
And that one we cancel the gradient and divergence.
Because the divergence of, it was with respect to
It's the
x, right?
prime, yeah.
With respect to z, it was a z component. You take the derivative with respect to z of the x dependency.
Yeah, so we cancel that out, but for M is in Z direction, so that one cannot be canceled.
M is not in the z direction, right?
It is.
M is in the x and y direction. J is in the z. Yeah, J is in the z.
Jesus, never mind.
Yeah, J is in and out of the board. M is circumferential.
Really?
Yeah. Right? It's TE polarization. So the electric current
Yeah.
is in and out of the board. Or TM to their book.
Yeah.
TM to Z, if you will. J is in and out of the board. M is in plane.
Oh, really? Okay.
But still, so H from M, you might have an X component with X dependency. If you have to differentiate
Oh, yeah,
that.
yeah, you're right, it's X direction, yeah, right.
X and Y.
Yeah.
We'll have to take a look at that.
Yeah.
What's going on?
Thank you.
How are you guys? What time is it? Good, thanks for coming. Did you get CST up and running?
Yeah.
It's working?
Yeah.
Good. Does it still have all that noise in the data?
Well, before simulating that one, I'm simulating some other papers that I'm sure what the results are. And
Okay.
today or one day, I expect to get the results on time.
Very good. All right. Oh my goodness. Okay, so let's go ahead and get started. So as a reminder, this lecture today is a pre-recording for next Thursday. And as another reminder, next Tuesday, we will not have class. So watch this lecture before next Thursday, and the next class will resume in 2 Tuesdays from now. Okay, great. So we left off last lecture looking at magnetization and permeability, and we're trying to develop a model for a magnetic dipole moment. So atoms that comprise of a material that can be magnetized contain atoms which have a positive nucleus and a negative electron that is orbiting the nucleus. And in this case, the orbiting electron creates a circular path, And because it's a charge in motion, we can constitute a current, or we can describe a current using that electron's orbit. And that path is circular and encloses some area that we're denoting as ds. So the dipole moment defined for magnetic materials is defined here. dm is equal to the current times the enclosed area. All right, so that's the magnetic dipole moment. So the more the current, the greater the magnetic dipole moment. The larger the radius of the path that the electron takes in orbit around the nucleus, the greater the magnetic dipole moment. So it's a vector quantity, of course. It has a direction. The direction is normal to the area of which is enclosed by the electron that is orbiting. So it's normal to the plane of the orbit. And it's proportional to the current and the enclosed area. Because it's only proportional to the enclosed area, it doesn't matter what the path or the shape of the path is. It could be a rectangular path or a circular path. So long as the area is equal, the magnetic dipole moment will also be equal. All right? Great. So over here, you can see a picture of a material. And this material has randomly oriented magnetic dipoles. So all of the electrons that are orbiting the nuclei are oriented, have their magnetic dipoles oriented in random directions due to thermal energy. And when there's no magnetic flux density applied to the material, the total magnetic moment is zero, if you were to sum up all of the magnetic dipole moments. However, when you switch on a magnetic flux density vector field and it permeates the material, what happens is a torque is applied to each of these magnetic dipole moments, tending to align them with the applied field. And in doing so, a net magnetization will occur. The magnetization is defined similarly to how we define the polarization vector field. Here we're defining a new vector field called M, capital M. And this capital M has a value inside of the material that's magnetized, and it's zero outside of the material, just like the polarization field P. And we define it in a similar way. Take the limit as the volume shrinks to zero in order to define a continuous vector field M, so we can assign to every point a magnetization. And we add up all the dipole moments per unit volume, the total magnetic moment, right? Total magnetic dipole moment. That's equal to, so we factor out the summation, and we plug in our definition for each dipole moment and sum them up for the unit volume. So here, the magnetization is exactly analogous to the polarization. We're summing up the magnetic dipole moments within a material and taking that volume to zero. All right? Great. All right, so assuming for each of the loops, we can define, again, an average magnetic moment, similar to how we did for the polarization vector field P. We define an average displacement, or an average displacement length. Here, we're going to define an average magnetic dipole moment by averaging IDS, so the areas that are enclosed plus the current. And therefore, we can define M in a simple way as N hat times the number of dipole moments per unit volume multiplied by IDS average, or the average magnetic moment. Then M has a simple form. That only, of course, works in uniform media. Okay, very good. So, of course, you can calculate the applied magnetic, the torque that the applied magnetic flux density applies to each of the magnetic moments. And that torque can be described similarly, or described in the following way. Delta T is equal to dm cross with B. So it's the definition of the cross or the torque. And the definition of the cross product for the magnitude of it, at least, magnitude A, magnitude of B, and the sign of the angle between them. And then, of course, we know what the magnitude of the dipole moment is. It's N hat IDS. And then we take the cross product with B. Okay, so we put it back in this form. And we can come up with the magnitude of the torque that's applied to each of these individual magnetic dipole moments. Of course, we need to know the angle between the applied field and each of the dipole moments. But luckily, we won't have to do that, right? It's the macroscopic model. Okay, great. Okay, so similarly to what we did for a polarized material, we had an electric field that polarized the material. It's a static electric field. It induced dipole moments, electric dipole moments, and all the neighboring atoms. So the nuclei of one atom and the electron cloud that was stretched from the atom just above it tended to cancel the net charge, right? So we were left with bound surface charge on the upper and lower surface of the dielectric. Here, we're going to have a similar thing happen, a similar cancellation. But here, we're going to have neighboring loops of current cancel. So what happens here is I have a magnetization M, which is the sum of all the dipole moments. It's a vector field continuously defined throughout the material, and it represents the magnetization of the material at any given point, right, by definition. So there's M there, and M points in the direction orthogonal to the current loops, of course, and the current loops are all aligned with the applied field B. Okay, if you look at any two neighboring paths of the current of the magnetized material, then these two paths are in opposite directions. And what happens is those two tend to cancel, and therefore, similar to Stokes' theorem that we studied in lecture 1, all interior paths cancel, leaving only the exterior, right? So the magnetization in this case, when it's a uniform material, is only a surface magnetization that exists around the perimeter of the material, right? So all interior edges of current cancel, leaving only the surface current on the perimeter. This is similar to the Stokes' theorem proof, called J magnetization surface. So it's a surface current density, and we call it JMS. It is this remaining perimeter current JMS that gives rise to M, right? So we can immediately see what we expect M to, or the form of JMS to be, right? There's an axis, M. There is a current that we're defining JMS. That's this current that circulates it goes around the perimeter of the material. And we expect M to be the axis of this current, right? Of the circulating current. So we know it's going to have a curl relationship. And we will define that. So JMS is going to be the curl of, or M will be the curl of J. Okay, so the magnetic flux density across the slab is increased by the presence of M. So we have magnetic flux density applied, and then we increase magnetic flux density due to the magnetization of the material. So within the material, we have a greater magnetic flux density than we do out of the material, right? At some point outside of the material, the magnetic flux density is mu naught H applied, right? Because this is the free space magnetic flux density of the applied field. So at this point, outside of the material, I only have the applied field. And mu naught is a constant that acts to convert or to represent the applied magnetic field in terms of a density, flux density, right? A vacuum, free space. But when I'm at points within the material, why is it only points in the material? Because M is defined only inside the material, it's defined everywhere, but it takes on a value of 0 outside of the material. And M only has a value in the material. So within the material, my magnetic flux density is increased by a factor of mu naught M, right? M accounts for all of the magnetized magnetic dipole moments, magnetized atoms. Okay, so one thing to note, there's a break in symmetry with respect to the electric polarization case, because remember before we had D, we defined D, so maybe I'll write it down and then erase it. So D was equal to epsilon naught E applied plus P. So the difference here is that epsilon naught only applied to E before, but now we have mu naught applied to M and H. So there's a slight break of symmetry, and that's because M, the units of M, are of that of a surface current, right? They're amps per meter. Okay. So let's work that out a little. We have B is equal to mu naught HA plus M, which is mu naught HA. Of course, we know that the magnetization is linearly proportional to the applied magnetic field, magnetic flux density, right? Linearly proportional to the applied magnetic flux density. So we expect a constant to proportionality, leaving a linear relationship, and we can again call that chi M. Then we can factor out the HA, similar to what we did in the electric case, and we get mu naught 1 plus chi M, and we get, we can call 1 plus chi M times mu naught mu sub S, which is the static magnetic permeability of the material, right? The applied field is static. Okay, and we can also define a relative permittivity above free space as mu static relative is mu static times, no, that's backwards, sorry. There's a mistake. This should be mu static is mu static relative times mu naught, all right? Make that change. Mu static is mu static relative into mu naught, right? Of course. All right. Okay, good. All right, so now we have this magnetic vector or magnetization vector field, right? And the magnetization vector field is accounting for all of the magnetized dipole moments, right? Because it is the sum of all dipole moments per unit volume. So M is accounting for, it's a continuous vector field that takes this discrete summation, if you will, of magnetic dipoles, makes it into a continuous vector field by defining the sum over a unit volume and letting that volume shrink to a point so that I can define this density at every point, right? So M is accounting for all of the dipole moments in the material. Now what we need to do is we need to find the field due to this M, because that's the whole point. What is the field due to these magnetized dipole moments, right? So to do that, we're going to do something similar that we did with the electric case where we calculated the scalar potential because we were working with the static polarization. Here, we're going to be working with the magnetic vector potential because we're working with a static magnetization, but that vector potential is due to a current, right? Okay, so we want to calculate the magnetic vector potential. The field at a point R, due to a magnetic dipole at the origin, can be found from the magnetic vector potential. So we have a magnetic dipole at the origin of a coordinate system, and we want to find, we have X, Y, and Z. We have some magnetic dipole moment here, right? At the origin, we want to find the field at some point R. Okay, well, we use the magnetic vector potential here, mu naught over 4 pi M, which is the magnetic dipole moment. So this is M here. M crossed with R minus R prime over R minus R prime cubed. All right, this comes from statics when you guys took your last class in electromagnetic field theory. So this generalizes when we replace M by MdV, right? So this same formula can be used to calculate the magnetic dipole or the magnetic vector potential due to a distribution of magnetic dipoles by integrating over the volume and representing M by MdV, right? Magnetic dipoles per unit volume multiplied by the volume gives you a magnetic dipole again. All right. And integrate over some volume, so we still get the same, we can use the same result. And then note that, again, we use the same identity here where R minus R prime over R minus R prime magnitude cubed is equal to the gradient prime of 1 over R minus R prime, right? And now we're going to use the product rule where curl prime of M over R minus R prime is equal to 1 over R minus R prime times the curl prime of M plus the gradient of 1 over R prime, R minus R prime cross with M. So where do we see this? Here. So forget about this part first. We just have, okay, let me see how we're doing that. Okay, so we have the integral over the volume of M cross with R minus R prime. We can represent R minus R prime, so this quantity here, as the gradient of something. So then we're going to end up with M crossed with the gradient of something, and that is here, this term here, right? M crossed with the gradient, if you pull out a minus sign, M crossed with the gradient of that, all right? So you use the other two terms in this identity to arrive at this formula here. Okay, good. So now the magnetic vector potential is equal to mu naught over 4 pi, integration over the volume, and these two terms. So we should have this term remaining, and then there should be a minus sign applied to this term because we had to pull a minus sign out of this term to make it M crossed with that, right? So this term went to their side, this one went to this side, it's here, right? So this term is negated. So both the terms are there, good. We apply the divergence theorem. It can't be the divergence theorem, right? What did we, copy and paste error again. So this has to be Stokes' theorem, right? Let's see, R minus R prime, curl prime of M dV minus, the second term. We convert from a volumetric integral of the curl into a surface integral. This is Stokes' theorem. Okay, Stokes' theorem. So we have these two terms remaining, right? We converted the second volumetric integral into a surface integral. So mu naught over 4 pi, the integral over the volume of 1 over R minus R prime, the curl of M with respect to the source coordinates, prime, minus mu naught over 4 pi surface integral of 1 over R minus R prime, M cross with ds. Okay, so what do we see here? What we see here is this is the potential due to a volumetric current density, right? The volumetric current density is the curl of M. So this J magnetic volumetric current density is equal to the curl of M. If you make that assumption, or if you make that identity that the curl of M is equal to J, then J over R minus R prime integrated is the magnetic vector potential. All right. And then we have the potential due to a surface current density, JMS, as M crossed N over the surface. If you plug that into here, then you also get a potential. They both have the same form, the form of a potential, right? Good. So what we have done is taken the magnetization. We want to find the vector field, or we want to find the field due to the array of magnetic dipoles. We want to find the field due to the magnetization current, which represents the array of magnetic dipoles, right? Because we want to find the field due to the array of dipoles. So we've now recast the problem into finding the field due to currents, and we know how to do that, right? That's easy. Once we know current densities, we can integrate those to find the field due to them. So we've taken this array of magnetic dipole moments, and we've converted them into currents that we can calculate the field due to, right? So that's so much easier than trying to add up the field due to all the dipoles. I could have started here and done a summation over the whole volume and found the field due to every one of the dipoles, which is a lot of work, right? We'd have to know the position accurately and the orientation accurately, the magnetic dipole accurately of all those magnetic dipole moments, but we could do it. Instead, we've recast the problem into finding the field due to current densities. One is a surface current density on the perimeter and the extremities, and one is a volumetric current density, which is the curl of M. So that's the power of what we're doing here. Good. Okay, so of course, how does this bound magnetization current work? The bound magnetization current IM flowing through a cross section S naught of the material can be obtained in the following way. We take this magnetization current, which has units of amps per meter squared, the same units as a surface or a volumetric current density, right? And we do the same thing. We integrate that volumetric current density through a surface, right? And we get the current enclosed. Same as when we convert Ampere's law from differential to integral form, then we integrate both sides of Ampere's law. We end up with the integral of J dot ds on the right side. And we can call that I enclosed, right? The current that penetrates this surface. Well, that's equal to the integral of curl of M dotted with ds, because Jm is equal to the curl of M, right? So we'll see that in action. All right. All right, so now that we're able to calculate the magnetic vector potential due to the array of magnetic dipoles, how can we use this to calculate the field, right? So to account for this current density, we modify Ampere's law written in terms of the true physical measurable fields E and B, right? E and B are what you can measure in the lab. D is a derived field, which is a mathematical construct, if you will, that allows us to calculate the fields the response due to materials that are polarized. We're going to define a new vector field in an analogous fashion called H, which allows us to calculate the response due to to materials. So the curl of B is equal to mu naught J plus J omega epsilon naught E. And so this is, so if you divided both sides by mu naught, you would get the curl of H. But here we're writing Maxwell's equations in the form of physical measurable fields, right? B and E. So the curl of B is mu naught J plus J omega epsilon naught E, which is partial D partial T. I feel like there's a minus sign missing. Curl of H is, no, this is correct. This is good. Yeah. Okay, mu naught. So this is the current of free charges, right? The conduction current. Mu naught J free plus J magnetization plus J polarization plus J omega epsilon naught E. All right. I think there's some arrows missing here. We'll fill them in. Okay, so what have we done? We've taken this current density J, we've broken it into multiple components. One is called the free conduction current, right? Because this current on the right side of Ampere's law, it can be broken into multiple components. One is the free current. Another one is the magnetization current that we defined on the previous slide. And another one is the polarization current due to electric polarization, right? And then we have j omega epsilon naught E. All right, good. So these arrows probably go here, right? There's a conduction current, magnetization current, polarization current. So fix that in your slides. All right, so let's fill in the definitions. The curl of B is mu naught J free. So conduction current, right? Electrons that are free to move about. That's one component of current that leads to a magnetic field, a curling magnetic field. The curl of M is J magnetization. J omega P, we defined on a few slides ago, the electric polarization current density, and J omega epsilon naught E. All right? Good. All right, we're going to group some terms like we did before. So J omega P plus J omega epsilon naught E, we can group into the following form. And we have J free plus curl of M, right? We know that epsilon naught E plus P is D. So we have J free curl of M plus J omega D. Now we're going to rearrange this equation and divide by mu naught. So we'll move the divide by mu naught, move curl of M to the other side. Why do I want to do that? I want to combine this curl with this curl over here. So curl of B over mu naught minus M is equal to J free plus J omega D. We're almost at Maxwell's equations, right? Maxwell's equations had the curl of some vector field is equal to J plus partial D partial T. But in time harmonics, it's J plus J omega D. So this is some new vector field that I'm going to define, right? This is due to materials. So B is what I measure in the lab. This is the Ampere law that is that comes from Maxwell, right? Curl of B mu naught J plus J omega epsilon naught E. Here, I've rearranged these terms that include the effective materials now. M is a material dependent quantity that characterizes magnetization of materials. And I've created a Maxwell equation now that's also valid for material, media, and free space. All right? What I'm going to do is call this B over mu naught minus M. I'm going to call it a new vector field. I'm going to create this new vector field called H. H is now B over mu naught minus M. So H is a derived quantity. It's not measurable. H is a field that includes the effects of materials, right? Okay, so we can now define a new vector field called the magnetic field intensity as a mathematical construct. It's not physically or directly measurable, which can account for the field, magnetic dipoles, and magnetization. So we have the curl of, so here's our new vector field H. We can rearrange this. Okay, so using this definition, this equation up here, which also valid in material media, is now the curl of H is J free plus J omega D, which is what you're used to seeing for Maxwell's equations, Ampere's law, right? But you didn't know that this form allows for to account for materials. And one more thing we need to note is the J that appears in Ampere's law is the free electron current density. It is not the bound charges. They don't contribute to the right-hand side of curl of Ampere's law. And on the same note, when we derived the form of Gauss's electric law, divergence of D equals to rho free, right? So the divergence of D, this new vector field we defined in the electric case, which was analogous to H that we're defining here in the magnetic case, was proportional to rho free, meaning that the bound charges, when I polarize a dielectric material, I have surface charge density that appears at the upper and lower surfaces. Those surfaces do not contribute to the divergence of D equal to rho free. In those cases, even when you have a bound surface charge density, divergence of D is equal to 0. And the reason is you cannot define an integration surface like a Gaussian surface to separate those charges from their host atoms. All right, so remember, divergence of D, rho free. Don't try to make a Gaussian surface for a dielectric and try to enclose the upper surface of the dielectric and have that Gaussian surface go through the dielectric and expect to see an electric field due to that. Okay. Rho free, J free. Good. Any questions? All right, good. Okay, so now we're ready to define magnetic susceptibility and permeability. So in linear media, we expect the applied field to be, which results, So we expect the applied field HA results in generally small polarization of molecules through rotation. And we expect a linear response to the field, right? We kind of already said this before. There's some proportionality constant from the magnetic applied field intensity to the magnetization, right? So in the electric case, we had P was equal to epsilon naught chi E into E applied, right? Here we're using H applied, right? There's no mu naught here. So what this says is it's a proportionality constant, right? So if you have a large magnetization, that means or a large chi, that means a large response to the applied field, and the medium is easier to magnetically polarize, right? Okay. Using the above, we can write our H field definition here, B over mu naught minus M, as B equal to mu naught H plus M. So all we have to do is multiply through by mu naught and then move that term to the other side. We get here. Then we can say mu naught is equal to, or M is equal to chi M times H. Then we can factor out the common H, and we end up with mu naught 1 plus chi M, and we can define what's called a magnetic permeability. The magnetic permeability, right? This is a dynamic quantity as well, right? Before we had static quantities. Okay, so mu naught mu r into H. So mu is a single constant which accounts for the field due to polarized magnetic dipoles within the medium. So we've recast the problem of trying to sum up the field due to a bunch of magnetized dipole moments or magnetized material, which is comprising of magnetic dipole moments, trying to find the field due to all of those dipole moments into a single constant. This constant accounts for all of that, right? That's what the permeability is. And typically, again, it's a measured quantity. Okay, so similar to how we define a time-varying electric current density or polarization current density, we can define a time-varying magnetization current density. So recall that to obtain the polarization current density, we referred to Maxwell's equations, right? The curl of H, here we're going to do the same thing. The curl of H, J omega D, or before, in the electric case, curl of H was J omega D, which is J omega epsilon naught E plus P. And then we factored the J omega, or distributed the J omega, and we defined a J omega P, right? Okay, we may try the same thing with the magnetic flux density equal to B equal to mu naught H plus M. And if we try that, we use Faraday's law. The curl of E is equal to minus J omega B. We know what B is. It's mu naught H plus M. And if we factor these two things, we find that there's a magnetization current called J omega mu H. All right? So partial mu naught M with respect to T acts as a current density, right? It acts as a magnetic current density because it's on the right-hand side of Faraday's law. Whereas J omega P, which is partial P, partial T, acted as a current density because it's on the right-hand side of Ampere's law, right? Good. There are instances where the time-varying polarization current is kept instead, such as the case of the boundary condition often used to model metasurfaces. So here, I'm bringing up the metasurface boundary condition again, how we model metasurfaces. Here we have an array of polarizable inclusions that when undergoing polarization, induce an electric and a magnetic dipole moment. And these electric and magnetic dipole moments may be polarized either by electric or magnetic fields, leading to what are called magnetoelectric inclusions or by anisotropy for the whole surface. All right? Now, the boundary condition which describes this array of polarizable inclusions is following. And now we see minus J omega mu M. We know what that means. That means that this magnetic dipole is oscillating and it's like a current, right? And J omega P means that this electric dipole is oscillating. They're all oscillating, right? And discretely, that electric dipole is oscillating. But we define P as a continuous summation. So it's a continuous vector field. So it's like a continuous sheet of polarization P, which is oscillating in time, which is a current. So it's a sheet of current, right? Okay. Permeability of common materials are listed in this table. We have bismuth, silver, lead, copper, water, vacuum air, etc. and they can be classified in different classes. One is diamagnetic, which means they slightly oppose. The permeability is slightly less than 1, less than free space, right? Then we have non-magnetic material, vacuum, has a permeability of 1. Then we have paramagnetic, means that it slightly increases the flux density, right? I apply a magnetic flux density to a material, it magnetizes, right? Does the magnetization increase the flux density? That would be paramagnetic. Does it increase it slightly, right? Does it decrease it slightly? So the material decreases the magnetic flux density inside due to the applied magnetic field. That's diamagnetic. And then we have ferromagnetic, which increases the magnetic flux density a lot, right? So mu is very large. And we can see our common magnetic materials here. Cobalt, iron, and there's mu metal with 100,000, some super alloy things, right? Okay. So the magnetization opposes the applied field in diamagnetic, and the magnetization supports the applied field in ferromagnetic, paramagnetic, antiferromagnetic, and ferrimagnetic. All right? Good. So let's do an example that kind of brings all these concepts together. So here's the example. A bar of magnetic material of finite length, which is placed along the z-axis, is shown in this figure. Okay, so let's get rid of that, right? Is shown. Has a cross-section of 0.3 meters in the x direction. So here's a bar of finite length. It's placed along the z-axis. So the z-axis is orthogonal to the material. It runs through it. It has 0.3 length along the x-axis and 0.2 length along the y-axis, all right? The bar is subjected to a magnetic field so that the magnetization vector inside the bar is given by m equals to z hat for y. So here is the magnetization vector. It points in the z direction. And we know that J is equal to the curl of M, right? So we expect, remember what the curl means. The curl means if I define an axis, I want to calculate the magnetization, I guess, in this case, if the vector field is circulating about some axis, right? I do the closed loop integral of that vector field around some path that has a normal vector that's normal to that area that I'm enclosing with that path. That normal vector is the curl that I'm calculating. So what it says is J, which is the current density, is the axis of which the magnetization circulates about, right? All right. Okay, so we have some M which is circulating about here, right? Or no, this is J. The J magnetic surface is circulating about the M, right? Okay. And one thing that we have defined in the problem is that this magnetization depends on position, right? The magnetization is changing strength as we increase in the y direction. So magnetization is in the z direction, right? Magnetization in the z direction, but its strength increases with y. So the y direction is this way, right? So as we move that way through the material, the magnetization is getting stronger. All right? What does that tell you right away about the material? I don't know if you can picture it. What does it tell you right away about the material? So we're applying, okay, so we've subjected it to a magnetic field. It is, it's inhomogeneous, right? It's not a uniform material. It depends. If we applied a uniform magnetic field and we got this kind of magnetization out of it, then that means that the material it's inhomogeneous, right? It's not a uniform material. So the magnetization is stronger at different parts in the material than it is at others, which means that the atoms are different, right, in different places. Or I guess another way this could happen is if you applied a magnetic flux density that had a linear gradient to it in strength. But anyway, let's assume that it's a uniform magnetic field, right? Okay, determine the volumetric current density, Jm, at any point inside the bar, and the surface current density, JMS, on the surface of each of the four faces, and the total current Im per unit length flowing through the bar face that is parallel to the y-axis. So this is the bar face parallel to the y-axis, right? All right. At x equal to 0.3 meter. Or sorry, this is the bar face that's parallel to the y-axis. Parallel to the y-axis. Okay, so the y-axis is this way. This face is parallel to the y-axis, and it's at x equal to 0.3. So it's this face. And we can see the flux drawn in it that is these arrows are this flux is penetrating that surface, right? So we can integrate that current density to find Im. All right, good. So J is equal to the curl of M, which is found through this following determinant. And what we find is that M only has a Z component for Y. If you do this calculation, then you only get partial by partial Y for Y, which is for X hat, right? So the magnetic volumetric, there's a volumetric current density here, right? Let's go back here and appreciate this really quick. Here, when we had a uniform material, right, means that M is the same everywhere in the material, right? What happens is the neighboring atoms cancel, and you end up with only a surface current density, which means that the volumetric current density, due to magnetization, is 0, right? There's no current in the volume. All of those loops are the same, right? Now, let's go here. We calculated that there is a volumetric current density, right? And what results is these magnetizations, these magnetizations are, they're not the same. They're not uniform anymore, right? They can't be because we have a magnetic current density inside, a volumetric. So because these loops are differing in size, they're neighboring, they don't cancel, right? This one's going up, this one's coming down, but they're different strengths, so they don't cancel perfectly. So I get this blue arrow here that represents the magnetization inside, the current density, Jm, right? The blue arrows are Jm. And you see that they exist inside now, right? What happens if these were all uniform? All these loops are the same size. These circulating arrows represent the macroscopic currents induced by the magnetization, right? If they were all the same, then there'd be no blue arrows, right? They would cancel. The volumetric current would put a 0, and this curl of M would give you a result of 0. But because the magnetization itself depends on Y, then it has a curl, right? The magnetization of these arrows, they get stronger in the Y direction. 4Y. M is equal to 4 times Y. So here is their axis of revolution is the Z axis, right? M is equal to Z hat 4Y. These are circulating in the XY plane. They have an axis in the Z direction, and they get stronger in the Y direction. So they do not cancel. So you get these blue arrows inside, right? So there's volumetric magnetization current density. All right, good. Let's calculate the surface current density now. M crosses N, evaluated at the surface. So what we do is we take M, we cross it with the normal vector at each of these surfaces, one at x equal to 0, one at y equal to 0, one at x equal to 0.3, and one at y equal to 0.2. And we do the cross product and evaluate the result along the face. So for example, at x equal to 0 is the back face here. And along the back face, x is equal to 0 everywhere, right? So let me try to, or let's do the front face because that one I can easily point to. Oh, okay, no, we'll do the back face. So here's the back face back here, right? Right? That's the back face. Along that whole back face, x is equal to 0 and y varies from 0 to 0.2. So x is equal to 0, y varies from 0 to 0.2. So my surface current density, JMS, which I calculate to be minus y hat 4y, is going to have a value that varies with respect to y, right? It'll be 0 at x equal, or y equal to 0, x equal to 0, because I plug in 0 for y, and it'll be equal to 4 times 0.2, which is 0.8, at y equal to 0.2. let's check that. Here's the y-axis. Here I have the perimeter, the red arrows are the surface current density, the surface magnetization current density. Due to this calculation that we're doing here, right? So it only exists around the surface. And what we see is, first off, at x equals to 0 along the y-axis, which is here, we have nothing when x is equal to 0, y equals to 0. And we have minus 4 y hat, or minus 4 y hat along the y-axis. So you can see these are pointed in the minus y hat direction, and they get stronger with increasing y, right? Okay. What about so that takes care of this surface. What about the surface at, let's say y is equal to, okay, so the next one we're going to do is y equal to 0. So at y equals to 0 is the face that we can't see, the one back there, right? That one has a coordinate y equal to 0 and x varying from 0 to 0.3, and we get 0 everywhere. So that's along this axis here, right? Y is equal to 0, x varies. And what we see is we get nothing over here. There's no red arrows in this region. And the reason why is the magnetization goes to 0, right? These arrows go to 0 there because the magnetization is with respect to y. So when y is equal to 0, you get no magnetization. So there can be no current at this surface because there's no loop rotating over here that has part of its loop or part of its path on the surface at that point. All right? Okay. Now, the surface at x equal to 0.3, which is this surface here, that one, we get y hat 4y. So here's all these vectors in the y hat direction, and they increase as y increases, right? Okay. Then we have this face back here, which gives you a constant current of 0.8 in the negative x direction. And we see these are all the same length, and they're in the negative x direction. Okay, so this picture here is a dynamic picture which completely describes this problem, right? So non-uniform material, we get volumetric current density, we get a surface current density, and because the magnetization starts at 0 and goes to some larger value, over here we have no surface current density associated with that. So part of the problem also was to find the magnetic current flowing through this surface of this face. And the way we do that is we integrate the current density dotted with ds, right? So integrate from 0 to 1. So we're talking about per unit length here. So we're going to do per 1 meter per unit length in the vertical direction, and 0 to 0.2 in the y direction, 0 to 0.2, and then 0 to 1, right? And then we're going to calculate m. So the curl of m dotted with ds, the curl of m dotted with ds, curl of m came out to 4x hat, dotted with x hat, ds in this case is going to be pointed, ds is a vector pointed out like this, which encloses an area that has dy and dz, right? Okay, so dy dz. And what we get is 0.8, all right? All right, good. Okay. Complex permeability. All right, so, so before we were talking about static, right? All the applied fields are static. So I might have said earlier on this slide, let me go back. I might have said earlier that this represented, that this was dynamic. This is static case still, right? Static case still, all right? Make that notation. So technically this should be a mu s. Okay, here, we're now going to introduce dynamics. So as discussed, the permeability of most dielectric material, including diamagnetic, paramagnetic, and antiferromagnetic material, is nearly the same as that of free space. All right, mu naught. Ferromagnetic and ferrimagnetic materials exhibit much higher permeability than free space. We saw that in the table. These classes of materials are also magnetically lossy, and their magnetic losses are accounted for by introducing a complex permeability. Okay, I want to clarify this real quick because now I'm even here. We define by using this relationship here, we were able to define a magnetic current density. And therefore, this might be dynamic here, right? Applied field. Why would this not? Okay, let me make a note of that. I'm going to go back in and check. I think this might be for dynamic fields, right? I think it is. It's not a mu static. So I said the right thing the first time. But now we're going to introduce loss by making this complex. All right, so the curl of E minus M minus J omega mu complex H now. So we have mu complex minus M, which is the impressed magnetic current density, right? We can impose a magnetic current density in space. Minus J omega complex mu times H. We can say this is minus Mi minus J omega mu prime H and then minus omega mu double prime H. This is the conduction magnetic current density. And this one's an impressed magnetic current density. This is the displacement magnetic current density, right? We can call all of that the total magnetic current density. All right, good. So what you'll notice is this one is a current density that has J omega time varying. This is a current density that's similar to sigma E, right? It's some real value multiplied by the field. So this represents loss, right? Loss due to heat or whatever. So we can also define a magnetic loss tangent in a similar fashion. The total current density is M impressed plus J omega mu prime into 1 minus J mu double prime over mu prime by factoring out J omega mu prime from here, J omega mu prime from these terms. And then I can say that that's equal to 1 minus J tan delta M now in an exactly similar fashion or analogous fashion to the electric case. Finally, note that the permeability is often a function of frequency as well, so it has dispersion. Okay. So that does it for our study of materials, right? Now we're going to jump into something I've added to the end of this lecture that might be something of interest for you guys, which is a discussion of metamaterials and how to design the permittivity of a material, right? So now you know what the permittivity of a material is. You know what arises from polarized electric dipoles or polarized dielectrics resulting in electric dipoles within a material. So how can we create artificial dielectrics? By imposing or changing or engineering the number of dipole moments that appear per unit volume within a dielectric material. All right, so this slide is introducing what a metamaterial is. So electromagnetic metamaterials are man-made materials comprised of structures whose electromagnetic properties are deliberately engineered to offer a range of response difficult or impossible to achieve in naturally occurring materials or composites. So here what I'm showing is a sodium chloride crystal, table salt. If you zoom into that table salt, what you'll see is a lattice, a periodic lattice, a unit, not a unit cell yet, but a periodic lattice of chloride and sodium ions. And if you zoom in even further, you'll see the crystal structure of that periodic lattice having some kind of cubic symmetry or I guess face-centered cubics. Looks like a cubic to me, to be honest. Okay, so, but the whole idea is this. This salt that you're seeing as a macroscopic response, see this crystal of salt, right? But here, what you see is when you zoom in, it's made of atoms. But when you observe it, you can't see the atoms, right? All you see is the average response from all of the atoms that are being excited by an applied field. So the observed response of light matter interaction from sub-wavelength atoms is an averaged one, right? If we probe this thing with a super short wavelength, like an electron, right? An electron wave function, then we might be able to resolve the atoms. Then we might be able to see them. Okay, say if you could, right? But instead, what we see is we're probing this with a wavelength which is much, much longer than the size of an atom. So we only see the average response from all of the atoms. So we're going to exploit the same principle in engineering some dielectric material that has a permittivity and a permeability, which may be a function of frequency, may be a function of time, may be anisotropic, it's a function of the direction of the wave. It may be inhomogeneous, it's a function of the position within the material, or it could be nonlinear, which is a function of the applied field strength, right? Okay. These properties are bulk properties, they're average properties. That's why we see just a cube, right? If you zoom into part of that material, you'll see that it's also made of a periodic arrangement of meta-atoms, we're going to call them. If you zoom into one of them, it's a meta-atom, right? Same principle. We're going to arrange these meta-atoms in a periodic lattice so that when we impinge a long wavelength excitation to it, then we don't see any of the atoms. We see the average response that we want to design, right? We want to engineer these parameters. But the thing is, we're going to illuminate this with a much longer wavelength, a lower frequency than we would with a material like this, right? This is being illuminated with visible electromagnetic waves or with light, visible light, and we're seeing the average response from that. Here we might illuminate this with microwaves so that we can make these meta-atoms much, much bigger, right? The meta-atoms have to be sub-wavelength, maybe lambda by 10 or less, right? So if we probe the material with a really long wavelength, then these will be big enough that we can manufacture them. And still we'll get the same effect as this and this, right? We'll only see the bulk average properties. So these meta-atoms can be made from different materials. They can be made from split ring resonators. We can make it out of a Swiss roll. These have magnetic responses, a resonant circuit, a loaded loop, so that we can have a very small miniaturized loop that has resonance frequency, and a chiral loop, which can rotate polarization or couple electric and magnetic dipole moments due to electric and magnetic fields, a loaded wire, or a dual split ring resonator, right? These are magnetic responses. These are electric responses, electric and magnetic. This has a magnetic response, and so forth. Now, all these are modeled using, for example, this loaded loop has a resonance, so we can model it using the Lorentzian dispersion, right? Lorentz model. So metamaterials exploit the light-matter interaction principles for ordinary materials and use them to design man-made materials with properties difficult to find in natural materials, right? So let's define what artificial dielectric is. It's sort of the first metamaterial that was ever constructed or conceived. And here what we're going to do is we're going to engineer the permittivity of a material by starting with a host medium and sprinkling it with inclusions. These inclusions are going to be sub-wavelength to the frequency of which we're going to operate this material at. And they're going to be polarizable, right? Say I use metallic spheres here and I put them in this array. And they have lambda by 10 spacing. And they're very small with respect to wavelength. Then when I illuminate this material or the artificial dielectric with a electromagnetic wave with a long wavelength, all of the, say it's vertically polarized, then all of the charges are going to, the electrons will rush to the bottom of the sphere, leaving the positive charge at the top of the sphere. That will create a dipole. So each of these metal spheres are going to create a dipole. And then by engineering their density and so forth, I can change the number of dipole moments per unit volume, meaning I can change P. Once I change P, then I can engineer E. So I can create an artificial dielectric this way, right? Okay, an artificial dielectric is a large-scale model of an actual dielectric obtained by arranging a large number of identical conducting obstacles in a regular 3D pattern. Under the action of an external applied electric field, the charges on each conducting obstacle are displaced. The obstacle is electrically neutral, normally without an applied field, so the dominant part of the induced field is a dipole field. Each obstacle, so each of these can be modeled as a dipole, right? Each obstacle thus simulates the behavior of a molecule in an ordinary dielectric in that it exhibits a dipole moment. This dipole moment, each of these dipole moments are defined as epsilon naught alpha dotted with E. So the induced dipole moment is linearly proportional to the applied electric field through what's called the polarizability of that inclusion, and the polarizability is a function of the geometry only. So different kinds of geometry give you different polarizabilities, and it could be anisotropic. So this is a tensor, and this technically should be E local, but we'll understand that in a second. So the combined effect of all obstacles in the lattice is to produce a net average dipole moment or dipole polarization field P per unit volume. Exactly how we analyzed ordinary dielectrics, where we said all of the atoms that comprised of the dielectric material were polarized and gave rise to a dipole moment. And then the summing of all those dipole moments per unit volume, when that volume shrinks to a point, converts this discrete summation into a continuously defined vector field, which we call P. So we can do the same thing here. All these dipole moments that are created by these inclusions can be averaged into a polarization vector field P. All right. The combined effect of all obstacles in the lattice is to produce a net average dipole polarization P per unit volume. If E is the average net field in the medium, the displacement field D is given by epsilon naught E plus P, right? Or epsilon E. P can be defined as the number of dipole moments per unit volume multiplied by the dipole moment itself, which is equal to P divided by ABC, where ABC is the unit cell dimensions, right? Each unit cell contains one atom, one polarization, one dipole moment, P, divided by ABC. And it's uniform, right? Okay, and it's apparent that the effective permittivity epsilon will be greater than epsilon naught because P is non-zero, right? Okay, good. Oh, whoops. So let's assume that there's a y hat polarized external applied field E naught y. Then the effective field acting to polarize the obstacle at the origin. So let's consider only the obstacle at the origin or the inclusion, which is this one. The field acting to polarize the obstacle at the origin is E effective y. So the effective field acting to polarize the obstacle is the external applied field plus what we're going to call the interaction field that we have to calculate. All right. The interaction field, the field due to all neighboring obstacles. So all these obstacles get polarized by the applied field, right? But remember, a dipole moment has a field associated with it, right? A scalar potential. That field also is felt by this atom, right? So all polarized atoms contribute to the field that polarizes this atom. But then when that atom becomes polarized, it generates a field that polarizes these. So these change, right? So there's some coupling that goes on. That's difficult to account for. Okay. All right. The interaction field due to all neighboring obstacles, is defined as the dipole field produced by all obstacles in the infinite array minus the field produced by the obstacle under consideration. So the field that's acting to polarize this obstacle is the field due to all other obstacles and the external field, but not the self field. This obstacle generates its own field, which is felt by itself. The dipole moment then is P equal to epsilon naught alpha E effective Y, right? This is our local electric field. And the polarization field P then is N alpha epsilon naught E effective Y, because this is P, right? And we had P equal to N times P vector, which is equal to N alpha epsilon naught E naught applied plus the interaction field. Okay. The interaction field is proportional to a dipole moment, right? It should be, because the field that this dipole moment, it doesn't radiate, but the field due to that dipole moment should be proportional to the dipole moment itself, right? And it's uniform. They all have the same inclusion. Every inclusion is the same. So the interaction field should be proportional to P. So it has some proportionality constant, interaction constant called C, and then divided by epsilon naught. All right. So how do we model the permittivity? P is equal to alpha epsilon naught E effective Y, which is E naught Y plus E incident or E interaction. We just said that E interaction Y is proportional to P through this relationship here. And then what we can do is we can multiply this all out and we get this expression here. And then we can find from one dipole moment the polarization vector field P by multiplying by the number of dipole moments per unit volume, and we get this expression here. Once we have P, we can use D equal to epsilon naught E plus P to find an expression that relates D to E, which will have units of permittivity in it, right? Sorry, here's kappa. So let me clear all this. Kappa here is the same as epsilon R. Kappa is epsilon R. All right. So we can use this expression to solve for kappa, and kappa then is equal to this expression here. Very important expression here. All right. So we can calculate what the permittivity is of our artificial dielectric material if we know what P is, and of course we have P here, right? And in order to calculate that, we need to know what the average field is in the Y direction. We need to know, we also need to know what C is, the interaction constant, and the dipole moment of one inclusion, plus the density of the inclusions, right? Okay, so let's calculate those quantities. Conducting planes can be inserted into the lattice at Y is equal to plus or minus B over 2. Why is that? Because of symmetry, right? So here's the Y-axis. Let's go back here. The Y-axis is here. We're considering this. There's an infinite array of these around it. So we're going to insert conducting planes here and here, right? So here are our inclusions. We insert conducting planes at Y equals to, or sorry, they're here. Here and here. These are the conducting planes. So on this last figure, the conducting planes would be here and here. All right. Because why can we only put them there and not, here to here, which is along the x-axis? Because the excitation we're assuming is in the Y direction, right? Y excitation. So we know that there's symmetry in the Y direction for sure. So we can put the conducting planes at plus or minus B over 2 plus MB, right? We can do that everywhere and we get the same problem. Image theory. We haven't learned image theory yet, right? So if I have a vertical electric field here or current density, then I can image it by placing conducting planes. We'll learn that later, all right? But no, we can put a conducting plane there. Since the applied field is Y hat E naught, the potentials at Y equal to plus or minus B over 2 may be chosen as negative E naught B over 2 and E naught B over 2. Why? Because we know that E is the applied field here, right? E naught. And we know that we have plus or minus B over 2 here for Y and minus B over 2 here for Y. So we can say that V, which is equal to E multiplied by D, we can say the potential here is E or E naught multiplied by minus B over 2 for the bottom here, and E naught times B over 2 for the upper surface, right? Okay, from symmetry on the planes X equal to A over 2 and X equal to minus A over 2, and Z equal to C over 2 and plus or minus C over 2, that's in and out of the board. The total electric field has no component normal to these planes. The total electric field has no component normal to these planes, right? Because of symmetry. Okay. This unit cell has to be the same as this unit cell. So there can be no electric field this way because this side would be asymmetric from this side. All right, the field in every unit cell is identical because it's an infinite lattice of identical inclusions. We know that phi is negative E naught Y because the electric field is applied in the Y direction and the potential V is equal to E times D, or E times Y in this case. Let's expand that potential. That's the potential in the central unit cell. Let's expand the potential due to all the other unit cells into a Fourier series, right? Cosine of 2 pi nx, cosine in the x direction, cosine in the z direction, and sine in the y direction, right? Because it has to be an even expansion in and out of the board and laterally because there are no field components that are in this direction, right? They have to be only in the vertical direction. There are no normal components of fields from unit cell to unit cell. And we know that, therefore, this must have even symmetry. This side has to be the same field as this side because of the symmetry in this direction. So it has to be an even function of y, right? Or z, or x rather, even function of x. But in this direction, we know that we have a negative here and a positive here for the potential, right? Because it's negative coordinates here and positive coordinates here. So that must have a odd symmetry. Okay, so the induced potentials here, right? Some unknown, so we have to add them all up, Fourier series. Okay, now we know that the potential and the electric field are related by a derivative, right? So E is equal to negative gradient of V or negative gradient of phi, negative gradient of phi. And the electric scalar potential only has a Y component, so it becomes minus gradient of, or partial phi I with respect to partial Y. And when you differentiate the Y component here, the sign becomes a cosine. Okay, now it's clear. If we average this electric field, we're trying to calculate E average Y, right? Because we needed E average Y. We needed E average Y here. So EP average Y. To calculate that, it's clear that if we average over one unit cell, it has even symmetry everywhere, the electric field. So we'll get a 0, right? Average of cosine over one cell is 0, right? Because it has, let's think about that. The cosine terms have a 0 average. Oh, I see. Cosine terms have a 0 average because they have the same. Seems to me a sine function would have a 0 average, right? 2 pi s over z cosine, if you integrate that over one period. Maybe when you sum them all up, and then these coordinates you're going to apply, but that makes it symmetric, positive on both sides. Okay, let me check into that. I know the result is correct, but I want to understand why. So you do get a 0 average field, right? Integrating cosine over a unit cell has a 0 average. Cosine of 2 pi n. Okay, so cosine when x is equal to a over 2. Okay, here we go. So when cosine of 2 pi, let's say the first cell, we get x is equal to a over 2. So we can't, okay, so a over 2 divided by a, that's equal to cosine of, the a's cancel, we get pi, right? Cosine of pi is minus 1, all right? Oh, okay, so we get minus 1 on this side of the unit cell. It's because of the coefficients in here. Okay, so we get minus 1 there, and then cosine of 2 pi negative a over 2 divided by a. We still get the same thing, right? Which is cosine of pi. So we get minus 1 on this side. And then cosine of 0, we get 1 here, right? So if you average that, so for a half cell, you would get 0, right? Because you get minus 1 here and plus 1 there. And here you get the same thing. Oh, yeah. So if you look at it like that, right? So break the cell into 2 parts. The left half, we're going to get 1 and minus 1 added together, you get 0. On the right half, you get 1 and minus 1 added together, you get 0. Still not, yeah, that makes sense, right? Because look at this. Duh. Okay, sorry. So here, we have this, and we go from here, minus 1. So let's say this is minus 1, and here's 1. We start from here, we go up here, and we go down here, right? That's one whole period of a cosine function, which has the integration of 0. So this negative half cancels with these positive halves, right? Duh, I don't know why. For some reason, I thought the integrating an even function, but I was thinking of only the half the period of it, you should not get 0. But if you integrate cosine or sine over its whole period, you get 0. Of course. Sorry for that. All right, good. But at least we're happy now. So integrating cosines, you get a 0 for an average. All right, good. Good. So we know that EPA average is equal to 0. So now kappa for this material is 1 plus P over epsilon naught E. We can plug in what we have for P from the previous slide. And we get this very well-known classical formula called the Clausius-Mazzotti relation. 1 plus number of dipole moments per unit volume, which is 1 over ABC, multiplied by the polarizability of the inclusion, divided by 1 minus the interaction constant times alpha, gives you the permittivity of your artificial dielectric. Okay? All right? So this is the Clausius-Mazzotti relation. Gives you the permittivity above the background host medium. So you might have some dielectric that's holding all these spheres in place. This kappa is relative to that permittivity. We need to know the atomic density, the electric polarizability of the inclusion, and the interaction constants. All right? So and it could be anisotropic. There could be XX, YY, and ZZ components. But here we're assuming symmetric particles. So we can replace a metamaterial in this case with an array of y-directed dipoles, an array of metal spheres with an array of y-directed magnetic dipoles. And we're going to calculate now the interaction constant. And let me jump ahead. Okay. What do we got here? So the interaction field here, we said is proportional to this interaction constant that we need to calculate. For unit dipoles, we know that the P, we're going to say, has a value of 1. We're going to call it a unit dipole. So E in interaction Y is C divided by epsilon naught. We need to calculate what C is, right? The potential due to a unit dipole at X naught, Y naught, Z naught is this formula here, because P is just equal to Y hat, right? And here's our R. The potential due to an infinite array of dipoles is found by summing the contribution from each. So this infinite array of dipoles, we sum these dipole fields over an infinite lattice. So over N, S, and M, from minus infinity to plus infinity, we're excluding the origin, right? Because we want the interaction field, which is the sum of the fields due to all dipoles except for the self term to the dipole of interest. And this is what that summation looks like, right? So here's our summation. The interaction constant is given by C is equal to epsilon naught E interaction by definition. And E interaction is the derivative, is the gradient of phi. So E is equal to negative gradient of phi. That means we differentiate this function with respect to X, Y, and Z, and we get this field here. We can sum that infinite summation by a trick known as the Poisson summation formula. And if we do that, sparing you the details, we get this for the interaction constant. These functions we're going to learn about next lecture. They're called modified Bessel functions of the second kind for cubical lattice. Don't worry about those for now. We're going to learn about these next lecture. But there's some special functions, all right? And for a cubical lattice, though, this reduces to C is equal to 1 over 3b squared. So that's what matters for us, all right? If the lattice is cubical, meaning that the inclusions are placed at the corners or the vertices of cubes, then this is our interaction constant, 1 over 3 times b cubed. Could be a cubed, could be c cubed. A, b, and c are equal. So for x-directed dipoles, A and B should be interchanged, while for z-directed dipoles, B and C should be interchanged, and so forth. Okay. So the permittivity then, this is our interaction constant, which we know is 1 over, is it 3? It's 3, 3b cubed. And then we can calculate the permittivity. Very cool. So now we know what the permittivity is using Clausius-Mazzotti. We know what the interaction constant is. We know what the atomic density is. It's 1 over ABC. We know what the interaction constant is now. It's 1 over 3b cubed. And all we need now is to calculate what the polarizability is of our inclusions. We can find the permittivity of our material. So the polarizability of these metallic inclusions the polarizability of a metallic sphere is known in closed form. It's known in closed form, and here it is here. So a sphere of radius 2r has a polarizability that is equal in both directions. So forget about this magnetic polarizability. It's equal to alpha EZ, so it's spherically symmetric, and it's equal to 4 pi r cubed. All right? So let the spacings be A. Cubic array of conducting spheres. Then the number of spheres per unit volume is 1 over A cubed, because it's even a cubical lattice with the same side lengths. The interaction constant, we know it comes out, you can evaluate these special functions, they come out to this value here, 1 over 3A cubed. And the permittivity known from Clausius-Mazzotti relation becomes the following. If you plug in this value here and this value here, you get this following closed form. So the permittivity is proportional to the radius of the sphere and the spacing, their density, right? How big the sphere is and their density. Okay, good. So let's do a test of that. Here I've ran a CST simulation where I have a infinite array. And the way I make an infinite array is there are periodic boundaries. This boundary and that boundary are periodic. This boundary and this bottom boundary are periodic, and the front and back face are periodic. So that means that it creates an infinite three-dimensional lattice. Of course, you can't really excite an infinite three-dimensional lattice in the simulation. So calculating basically eigenmode or the phase or the unit vector of K that we'll learn about next lecture across the unit cell. All right. So at 20 gigahertz for A equal to lambda by 10, this is A. As a function of the radius R of the sphere that fills up that unit cell of size A, I vary the radius for a fixed unit cell A, and I calculate using Clausius-Mazzotti what the permittivity should be. Epsilon R is here, right? So I can change the permittivity from free space all the way up to about 2.1 by changing the size of the sphere inside of that material, right? Okay, now what I'm comparing here is the CST Microwave Studio simulation of the phase delay across that dielectric, right? If I have a dielectric block here, let's say like this, and I calculate what the wave vector should be across here, K multiplied by D, let's say D is this dimension here of the phase. Well, K is 2 pi divided by lambda, and then we have D here. That's going to give me a phase delay phi, right? And lambda here is the lambda in the dielectric. So this is 2 pi divided by lambda divided by square root of epsilon r. So multiplied by square root of epsilon r times D. So you can see that the phase delay is directly proportional to the permittivity, the effective permittivity of the sphere loaded unit cell. So I calculate the phase delay in CST Microwave Studio. I can export directly what the phase delay is as a function of the sphere radius. And I calculate what the Clausius-Mazzotti phase delay should be for that same sphere using Clausius-Mazzotti formula. And what I get is perfect agreement. So Clausius-Mazzotti is pretty accurate. This is a numerically obtained solution, CST Microwave Studio. And I could use this back of the envelope Clausius-Mazzotti formula that predicts the permittivity of an effective permittivity. So we've homogenized it, right? We've assigned epsilon r to the whole material as a continuous permittivity, a single constant across the entire block, across the entire material made of spheres. So I take this metallic sphere in a unit cell, an array of metallic spheres, and I homogenize it and assign it a single permittivity. And then I calculate from that permittivity what the phase delay should be across a cell. And then I do the simulation. So this homogenized, Clausius-Mazzotti is a homogenized model. CST Microwave Studio is the exact numerical solution of the actual spheres and what phase delay you would get with that without doing any homogenization. And the numerical solution agrees very well with the homogenized model. So I can homogenize the metallic spheres into a continuous permittivity, and I can calculate that with Clausius-Mazzotti, and it behaves exactly the same as a continuous solid block of dielectric material permittivity epsilon r obtained from Clausius-Mazzotti. All right? So yeah, here's KD, right? There should be a D here. That's how we calculate this KD here. We export KD from simulation for the spheres, and then we homogenize everything calculated by Clausius-Mazzotti and calculate, using that homogenized permittivity, what KD should be. And they match up very well. All right, so that was for metallic spheres. We'll end here, and please watch this video. I will be gone all next week at a conference. I'll return for lecture the following Tuesday. So the next Tuesday that will be at lecture, of course, you know, if you check the syllabus, will be the 19th is the next lecture. All right? So I'll see you guys then. Thank you. All right.
Thank you.
Yeah, thank you guys for coming. See you guys.